Okay, so for this lecture, as you can see, it's going to be sort of computer based. I'm going to go over some of the theory from the week one session two. That theory is kind of contained in the first one, just a little bit more precise here or more general. But I'm also going to talk through some of the programming things I do, and this is hopefully going to help. It's either going to help. I hope it's either going to help reinforce some things that you might already know, or if you're not very comfortable with programming, then hopefully this will help with that. Also, a lot of you guys have a lot of experience with this sort of thing, so if you see me doing something that's less efficient or maybe a better way of doing something, maybe I've gotten into some bad habits and I don't know about it yet. Okay, so what we're doing here, linear regression. So when we do linear regression, and we are really going to see this in week two. When we say linear regression, we don't mean that the model is linear. So like here, the model is ax plus a1. Here, the model is bx squared plus b1 plus b2. So we don't mean the model is linear, but we mean that it is linear. Like we don't mean it's a linear function of the predictor variable x. We mean it is linear in the coefficients or the parameters of the model. So here, this is linear in the a naught and the a1, and the b naught, the b1, and the b2. And essentially, what we mean by linear, it's the standard form of linear. It's the standard definition of linear. But for us, how we want to think about it is that we can write, if we have data, then we can write this whole system as a matrix vector multiplication, where the vector we're multiplying by are going to be the coefficients here. So that's the idea. So just like we did last week, we're going to illustrate how we can do linear regression with this load cell data. So again, a load cell is you have some sort of device and you put a load on it, and this load cell measures some sort of deflection. There's different ways. There's different types of load cells. Sometimes it measures some electrical property. Sometimes, I think I mentioned in the session one notes, like a scale is a load cell. There's like a spring-loaded thing, but it measures deflection in some sense. Now, the NIST data doesn't tell us what deflection means. It just says deflection. So we're just going to forget about exactly what the units are and just notice and just observe that when a load is put on the load cell, we know what the load in this construction to calibrate the model. We know what the weight is. We know what the force is, and then we're going to measure the deflection. And from that, we're going to try to get a model. And then in practice, what's going to happen is we're going to measure the deflection, and from that, we're going to figure out what x is. So in the first part of these notes, what we're going to do is linear regression to figure out what the coefficients b0, b1, and b2 are. And then in practice, if you're actually using this load cell to measure something, we would be measuring this output here, and then from that we would solve this quadratic for x, and that would give us an estimation or an approximation for the size of the load. Obviously, there's two solutions to a quadratic. Well, unless they just happen to be the same one, but there's two solutions to a quadratic, and so we will have to do something to figure out which solution is the right one. Okay, so the first thing that we're going to do is we're actually going to go and get the data. We're going to load the data in. So before we do that, we're going to do a few import statements. So I'm going to do import numpy is np. And so Python is a programming language, and just sort of bare Python can do a whole lot of stuff, but there's all of these packages that we can use that have functions within them and features in them that we can use that are not part of the standard, like, in the box Python package. They're just not part of the standard Python language, but they're packages that are added to it. And so because of that, we're going to import some of these packages. So NumPy is going to help us manipulate and do computations with arrays. Pandas is Pandas is a package that lets us manipulate data. So there's other packages that do this as well, but Pandas is one of the popular ones. And then we're going to do import matplotlib.pyplot. Okay, and I know some of you at least had some MATLAB experience. Matplotlib is supposed to simulate some of the plotting in MATLAB. Now, when we want to reference functions that are inside of these packages, we have to write like numpy dot whatever the name of the function is, or pandas dot whatever the name of the function is, or this dot whatever the name of the function is. Obviously, we don't want to do that, So when we say import numpy as in p, that just lets us write in p in the place of numpy. So instead of having to write like numpy.least squares, we can just write in p.least squares. Now there's a couple of other imports that are just sort of specific for today's lesson, for this week's lesson. I mean, in the sense that it's not part of the NumPy pandas and pyplot are going to be things that we sort of use throughout this semester to do things, like mathematically. This next part, import requests, and from IO, that's in out, import string IO. Okay, this is just to be able to go to the NIST website and get the data. Okay, so the URL where the data is stored, URL is going to be equal to, I'm just going to copy and paste this. So if we actually look at what this is, this is the data right here. Okay, so obviously this is kind of like some header data, and then we just need this part right here. Okay, and so now what we're going to do is the pandas library has a very powerful function for taking data and converting it into a data frame, which is just kind of what it calls its database essentially. It's like a or data table. That's what it's called in pandas, is a data frame. So we're going to say df, which again is data frame, is going to be equal to pd.read CSV. Okay, so df stands for data frame. What this function returns, this read CSV function, it returns a data frame. We'll talk a little bit more about that today and as the semester goes on. And so what we need to do is we're going to do, this is something that I had to look up because I do not, it's not something that I do a whole lot. Response.text. Okay, so oh sorry, there's one step that I forgot. So response is equal to, and it's exactly this, request.get URL. So now what's going to happen, this requests is a way to do internet things, to go to websites and get stuff. And so when we do request.get URL, what is stored in response here is just this data right here. So if we come here and look at view page source, well, okay, it's exactly like this. That's what it is. It's not an HTML file or anything like that. And then if we come over here, I'm actually going to just do something really quickly. If we print response.text, okay, so what's happening here, response is going to be a request.url returns several things. One of those things is the text of whatever is at the web page. And so response.text gets us that text. And so by running this, it's going to print something that's essentially going to look like this, probably formatted a little bit differently. But okay, so this is exactly what we get. So actually it's formatted exactly how we would want it to. But now what we're going to do is we're going to use pandas. We're going to use pandas. Whoops. There's going to be an error there. We're going to use pandas to read in this and put it into a data frame or a database. Okay, so now we have to sort of tell it how we want to separate the data. So this right here, the separator, this is a regular expression, and I'm not going to tell you too much about it because it's not something that is going to be that useful to us, but it's just going to separate the data based on a new line. Okay, and then we've got skip rows equals 60. We're doing this because the data starts at row number 60. And then the names of the columns are going to be deflection. The names equals deflection and load like this. Okay. And now what we're going to do, I'm going to do print df.head. This is just going to give us, I think, the first 5 entries of the data frame. This is really just to make sure that everything is working properly. Okay, so this gives us the first 5 rows, and we can come over here and see that, yes, these are the first, let's see, 1, 2, 3, 4, 5 rows, and it is what we have here. So this just gives us confidence that we've done everything correctly. And if we look at the tail, that's going to be the last. Okay, and again, we can come over here and look at the last of the rows and see that, yes, the last 5 rows are what is reported here. So everything has worked well so far. And the next thing that I'm going to do is print. I want to know how many rows. And there's a Python function that just sort of is very general. And you put whatever it is you want in there, and it tells you what the length is. Okay. And so that could mean this is a little bit different than like size of in C, which is not going to be the exact same thing. This just sort of whatever argument is you put in there is going to tell you what the length is. And so it says the length is 40. Obviously, the length, what type of thing this is, whether it's a string or an array or whatever, or a data frame, the length is, it's how length is interpreted is based on whatever goes there. So if you put a data frame there, it knows to return the number of rows. And that's exactly, that confirms exactly what we have here, because somewhere it says there are 40 measurements. It's either here or maybe I wonder what this. Well, okay, it's maybe there's like a page that describes this data. Maybe there it says how many entries there are, but there should be 40 entries. I don't know if it says it here somewhere. Okay, no, I don't. Oh yeah, 40 observations. There we go. Okay, so it says 40 observations. This says we have 40 rows. So again, this makes sense to us. Now you might be a little bit confused. Why is the last entry 39? This is the 39th row. Why is it 39 and not 40? Well, remember that Python is 0 index. So the first index is going to be equal to 0. Okay, very good. So this loads the data. We've sort of verified. It looks like it has the right data loaded in there. Okay, so in session 1, we started with the linear model and then upgraded that to the quadratic model. If you look in the notes, and if you look in the notes from session 1, so Math 647 week 1 session 1, we start with the linear model and we upgrade it to the quadratic model. Well, there's even a simpler model. We can start with a constant model and upgrade that to the linear model and upgrade that to the quadratic model. And as we will see in week 2, we're not always going to be upgrading to higher degree polynomials. We're just going to be adding other functions in there. Okay, and determining which functions to add in there, this is part of what we have to do when we're doing the data analysis. So the simplest model is a constant model. We haven't even discussed that yet. And so if the linear model is a naught x plus a1, and this is the quadratic model, then the linear the constant model is just going to be y hat constant is equal to a naught hat. One thing I want to mention about the hats, the hats are there. There's can be sort of slightly frustrating notational inconsistencies here. And the hats are there because we want to denote that these are the coefficients that we find when we do regression. Okay, because this is the linear model. It's not going to exactly fit the data, but these are going to be the regression coefficients. Anyway, so if we have a constant model, this is what we're going to have. Now, if we go back to what we talked about either in the session 1 video or the session 1 text, there's a matrix vector system of equations with the y vector on the left-hand side, and then the matrix times the coefficient on the right-hand side. Okay, in this case, the matrix is just all ones, and we just have one coefficient. So remember what we do, we multiply both sides by the transpose of this matrix. So by the way, the vector 1 is just the one, where it's just the vector of all ones for whatever length y is here. Okay, so then we multiply both sides by 1 transpose, and we solve this equation. Now what's happening? When we do 1 transpose times y, this is just the dot product of the all ones vector with y. In other words, it's just the sum of the entries of y. Similarly over here, when transpose dotted with 1, this is just the sum of the entries in 1. Well, what is that? You're just adding up 1 the number of times, for whatever the length of this vector is. If you say it's equal to n, which in this case is equal to 40, then we're just going to get 1 plus 1 plus 1 n times, and so 1 transpose times 1 is just going to be n, which in this case is 40. So then what we have on the left-hand side is this is going to be the sum of all of the y entries. This is going to be just n, and this is going to be a naught. In other words, a naught is going to be equal to 1 over n times the sum of all of the y observations, which is just the sample mean. Okay, so in this case where our constant model is equal to a naught hat, in the case where the constant model is equal to a naught hat, then in the case of a constant model, then a naught hat is equal to the mean, the sample mean of the y's here. Okay, and so that's what we're going to do below. We're going to code this in the cell below. We're not going to use polyfit here. I haven't even mentioned polyfit yet, okay, but we're not going to mention polyfit here because we'll do polyfit when we look at linear and quadratic models. For now, we're just going to say a naught is going to be the mean of the y variables. Okay, and now you can see here that Gemini is already telling me what I should do. Now this, I think, is exactly what we want to have happen, but also sometimes it gives bad suggestions. So I'm just going to type everything. So np.mean, and then we're going to do df deflection. Okay, so I'll explain what some of this is as well. Actually, I'm going to make this a little bit different. So I'm just going to run this. I'm going to actually change things just a little bit than how I did it in the notebook. So if you can't tell, this is just the week 1 session 2 notebook where I've deleted all the code, and so now I'm going through this with you. And so one of the things that I want you to do when the notebooks, when you open it up and go through it, I want you to modify things and change things and see how things change, as you change the model or whatever. So because I'm going to be using deflection a lot and load a lot, I'm going to come up here and I'm going to say x is equal to df deflection, load. So we've got the x variable, which is our load, and our output, our y variable, which is the deflection. So the response is deflection. The response or output is the reflection. And then the predictor or feature is going to be the load. So typically x is the independent variable, so x is the predictor or feature, we call it different things, and then y is going to be the response. In this case, y is the load, the deflection. Whoops. Okay, so one of the great things about Python, it's such a high-level language that the things that we want to have happen typically happen in the way that we want to have them happen. Okay, so what do I mean by that? Well, I want to look at, I want x to be the column of this data frame here. That is the load column. So for example, I want the load column to be this column right here, and I want the deflection column to be that column right there. Well, in the data frame, the load column is called load, and the deflection column is called deflection. Indeed, I can do df dot print df dot columns, and it's going to give me all of the columns. So deflection and load are the two columns that I have. In week 3, we'll look at a data frame that has more columns, and for the homework, the data frame that you'll get initially will have more columns. Okay, so x is going to be load, and y is going to be deflection. And because I want to make sure that I am dealing with a NumPy array, I'm going to do the following. I'm going to say dot to NumPy. To NumPy. There's an underscore there. Okay, so now x is going to be a NumPy array that's equal to all of these, and y is going to be a NumPy array that's equal to all of those. So for example, if I print x, what we see here, this is x, it's this list right here, and we could look and see it's exactly that list. And similarly, if I do print y, we're going to get, this is the y list as well. So if you look at the y list, starts here, ends at 2.168, and that's what we have here. Anyways, we don't need to have those printed each time. So let's go back to that. Okay, so then down here, A0 is going to be np.mean y. So again, NumPy has this great, it's ways, NumPy is a library that gives us ways to work with with NumPy arrays, and so there's a great function called mean. We just do np.meany, and it gives us the average, the arithmetic, the normal average of y. Okay, and so now what we know then is our model is just going to be y is equal to this mean here. So let's plot the model and the residuals. And I'm going to do a couple of things first because I haven't shown you how to do this yet. So first, I want to do a scatter plot, or I haven't shown you how to do it in a video. So PLT is the library that has all of the plotting functions. So I'm just going to do a scatter plot x and y. Okay. So plt.scatter gives us x and y. There's other different functions to do other types of plots. Okay, perfect. Now, one thing that we don't want it to print this, and we also want it to print a title and stuff like that. So what we can do then is plt title, and we're going to put the title here. So I'm going to say load cell data. Okay, got that. Still have this. We will worry about that in just a little bit. So we're going to do plt.xlabel. So I'm just going to put tab. Press tab. Okay, Gemini's already telling me what I want. We do not know the units here, so we're going to get rid of the units. So there's where Gemini kind of got it wrong. But plt.xlabel is load. plt.ylabel is deflection. So x label means horizontal and y label means vertical. I would rather have like h label for horizontal and v label for vertical, but x and y works as well. And then this plt.show, what it's going to do, if we don't have plt.show, then the sort of standard way that Python is going to print something is it's going to tell you like this right here, which is like sort of metadata or something about the table, and then it's going to print the table. But if you do plt.show, it's just going to print this. Sorry, it's just going to print the table without that. Okay, so that perfect. That's what we want there. Now, what we're actually going to be doing, we want two plots. We want a plot with the we want a plot that has the load cell data and a constant model. That is, we'll have the load cell data with the model curve plotted on top of it, and then I also want to plot the residuals. And sorry, I just realized there's something wrong in there's something not exactly right in the notes. So hold on one second. Let me fix that. Or there's something not quite right in what I had before. I'll mention what it is right now. Okay. Yeah. So again, the code here is going to be a little bit different than the notes, anyways. Okay. So now what I want to do is I'm going to do this in a couple of steps. I want to plot the curve on top of this. So the way I can do this is to do plt dot plot. This is the way plt dot plot works is we're going to give it an x vector and a y vector. Those have to be the same length. At each one of those points, it's going to draw a dot, and then it's going to connect them with a line. Okay, so we've got plt dot plot, and we want to have x, and then what we want to have now is a0 times np dot ones like x. Okay, so what's happening here? Okay, so again, plt dot plot. If I just do, let me actually just do it like this. If I do plt plot x comma y, like between all of these points here, basically it's just going to draw a line segment. And so if we do this, here's what we get. If we just look at the line, this is what we get. Okay, so this isn't what we want. So if we want to plot the model, the y values, it's going to be the same y value no matter what the x value is. Okay, and so what's going on here? np.ones like x. So this ones like function is very, very convenient. It returns a NumPy array of the same shape, that is the same dimensions as x, of all ones. And now we're multiplying it by a0, so it's going to be the vector of all a0s. In other words, we're going to look at all of the ordered points, x comma a0, as x goes through all of these load values here. And so it's just going to be a horizontal line. So that's what I'm going to do now. Okay, I really want this to be a different color, so I'm going to do color equals red. Color equals, got to put it in quotes here. Okay, so there we go. So these are the data, and this is the model. So notice what this model is predicting. It's predicting that if the load is 2.0, then the deflection is going to be whatever the mean is here. If the load is 3.0, I said 2.0, but it's times 10 to the power of 6, so keep that in mind. It says if the load is 3.0 times 10 to the power of 6, then it's also going to be whatever this mean is. So this is obviously not a great model, okay, but the average is used a lot in your life for a number of reasons. It sometimes can be a good way to approximate things. Okay. It doesn't really do a whole lot for what we're trying to do in this this setting here, but nevertheless, it's something that we can start with. Okay, so now what I want to do is I want to plot this and the residual. So I'm going to have two plots, the load cell data here and the residuals there. So what I first need to do is get the residuals. So I'm going to say E constant is going to be equal to the deflection, Y, minus the prediction, which is going to be A, or times the model, time minus A0 times NP.1 like X. Y. Yeah. Okay. So again, this is the predicted Y values, and these are the actual Y values here. Okay, and so now what I want to do is I want to do subplots, and this is exactly what's going to happen here. So we're going to do fig, comma, axes equals PLT dot subplots. Whoops. Okay, and I want the number. I want one row and two columns, and then fig size is equal to, I'm going to do 10 comma 4. This gives us the ratios. Okay, so I'm going to have two things side by side. So axes tell us in which location we're doing the plotting. So here we have one row and two columns. Okay, so if I just do axes 0, the 0th index is going to give me the leftmost, and then axis of 1 is going to give me the rightmost. Okay, so axis 0 is going to be very similar to what I have done before. Scatter XY. And then axis 0 dot plot, and it's just going to be this right here. Okay, I'll set the labels in just a minute here. Okay, so this is going to give me the this right here. Axis 0 is going to give me basically this model right here. I'll need to add the labels here in just a minute. And then axis 1 dot scatter, we're going to do X constant like this. Okay, and then we're going to get two plots side by side. PLT dot show shows everything. So hopefully, okay, so perfect. This gives us the residuals. It's exactly what we should expect because it's a constant model, so the residuals are basically just going to be this data here but shifted. Sorry. Okay, so now we just want to label it. So label the axes. Axis 0. Only now we have to do set title. Okay, all of this right here. Okay, perfect. Does this all for us. So we have to do set title, set X label, and set Y label. Those are just the functions inside the axes object. Okay. And then we're going to do the same thing here. Axes, perfect. All right. Very good. Perfect. The residuals are all centered at 0 exactly as we expected and has this line shape as well. Okay, well obviously this isn't a very great model. It looks like a line, so it seems like we should be able to just, fit a line to this and have everything work like we want it to work. And so that's what we're going to do now. So I already have our A constant up here, A0 up here, but because we're going to be doing this in more generality, we're going to do things a little bit differently down here. So I'm going to start with A constant, and instead of just saying this is equal to the mean, I'm going to use a new function called polyfit. So np dot polyfit, and we're going to look at x, y, and the degree is going to be equal to 0, so it's just going to be constant. this is exactly what we did up there, but there's a function that does it. So this is just how we do, if we want to do the least, if you want to do least squares regression, with where our functions are going to be polynomials, then there's this function in NumPy that does it. It's called polyfit. Okay, and now I'm going to come down here and I'm going to get predictors. So y constant. Okay, so here's a really cool thing that we can do. We'll see one way to do what we need to do in this class, and then in next week we'll see another way that we can do this. But what we're going to do is the following. We're going to say np dot polyval, and we're going to give it a constant and then x. Okay, so what is this doing? So a constant, np.polyfit returns a vector. It returns the vector of coefficients. If it's a third degree polynomial, it's going to return 4 coefficients. If it's a quadratic polynomial, it's going to return 3 coefficients. If it's a linear polynomial, it's going to return, or if it's a first degree polynomial, it's going to return 2 coefficients. And if it's a 0 degree polynomial, it's going to return 1 coefficient. Now what polyval does is it takes a NumPy array or any kind of array here, and then if there are 33 entries in it, it's going to create a 32 degree polynomial. And it's going to be the 0 index term times the highest degree polynomial plus the 1 index term times the second highest degree polynomial, and so on and so forth. And it's going to apply that to whatever vector you pass in there, which for us is x. Okay, so when we run this, y is going to be a vector where it's just going to be a constant. That's it. It's just going to be the a constant vector. Okay, so we're going to look at the residuals. Y constant is going to be equal to y minus y constant. Okay, so now we're going to do the same for a linear model as well. So we're going to do a dot linear is equal to np dot polyfit. But now we're going to do x, y, and now we're going to do degree is equal to 1. Okay, so now we're going to do y. This is the fitted model, np dot polyval, and we're going to have a linear x. What did I misspell? Oh, there we go. Okay, and then we're going to have e linear is equal to y minus y. Those are going to be those are the residuals there. Okay, and so now we want to plot this just like we did before. Okay, so now we're going to have 4 different plots. Okay, we're going to have the top row that has the constant model, and then the bottom row is going to have the linear model. Okay, so we're going to have fig axes is equal to plt dot subplots. It says 2, 3. That's not right. We want 2, 2. I don't know where it's getting that from. And I'm going to do for fig size, I'm going to do 18, 10. You could just look up and play around with what these values are to get a good layout. Okay. And now something is not happening right here. Oh, I forgot a comma here. Okay, there we go. Okay, so nothing should happen now. All right. I don't know why it's taking so long for nothing to happen, because it's having to do this. Wow. What in the world? I make way more mistakes when I'm doing videos than when I'm not doing videos. That was supposed to be here. Okay, yeah. Anyways. Okay, so now since it's a 2 by 32, there's the problem. 2 by 2 is what we want. Okay. Anyways, since it's 2 by 2, there's rows and columns. There's not just one column or one row. When we do the axes, we have to give it 2 different coordinates. So axes 0, 0 dot scatter. Okay, and we're gonna do x, y. And we're going to give it a label. Label equals observations. Okay. So then we're going to do all of these other things. This is great. So let me just talk through. So, okay, so Gemini is doing very great. for us, right? So the top left path is going to be exactly, sorry, the top left plot is going to be exactly this. Okay, and then we're going to look at the top right plot. Oh, let me set the title. Okay. All right, and then now we're going to do axes 0th row, first column, and then all of this stuff right here. So I'm going to change this. Okay, perfect. And again, what's happening here, we're plotting the x values against the residuals. Okay, and the zeros tells us, sorry, the first entry tells us what row we're on, and this tells us what column we're on. So we're on the 0th row, first column, 0th row, 0th column. So when I print this, it should print 4 plots. 2 of them are going to look roughly like this, and 2 of them are just going to be blank because I haven't done anything there yet. Okay, so there we go. Let's see, maybe, hold on 1 second. Oh, went the wrong way, hold on. Trying to make them look a little more square or a little more like this. Square is not really something that, anyways, okay, I'm going to leave it like this. Okay, so now I'm going to do the same thing. Axes, first row, 0th column, dot scatter. Again, we're going to plot x, y. I'm going to not worry about the labels for this because it's not, okay. Okay, I'm going to get rid of the labels for now because I didn't, you know what, sorry, I know why. Yeah, okay. I was like, it's not showing up and I don't feel like figuring it out right now, but here, let me just look at this. Yeah, okay. I'm not sure why there isn't a legend on this one yet. Oh, because I didn't put a label. Man, okay. And then here, oh no, these are the residuals. And then, yeah, you know what? I see now because I didn't actually plot the data. Sorry. I've done all of this obviously, but I still get a little bit, when I'm explaining it, there's things that okay. So let me look at this. It gives me a warning because there is no legend here. There's one other thing that I want to explain. This line right here is because I did this this H line right here, AXH line at 0, and because we want to see if the residuals are scattered, evenly about 0. Okay, so now we're going to do here label equals observations. Okay, now we're going to do X in the linear model, and I'm going to do the color as red. You know what? I'm going to protest and do not green. Okay, it's my way of protesting Gemini. Okay, and then I have label equals model like this. Perfect. Label is equal to the linear model, and now we're going to set the titles. And so we've got axes 10 dot set x label. Wow. Load, then axes 10 dot set y, and then the title. So most of the Python code is pretty clear what's happening, though obviously knowing that this is what you need to do is where where the challenge comes in. And then once you get more practice, of course, you will understand exactly, you'll have a better idea for the things that you need to do and at least what you need to Google. Axes 1, whoops. X comma E linear, and then all of this other stuff as well. Okay, I didn't mean to do that, but all right. So now everything should show like we want it to. Okay, so this is great. We see, obviously this red model does not fit the blue data very well. I'm actually going to come back here and make it green. Okay, so this green model this green line does not fit the data very well. Now, if we didn't have the residuals and we just looked at this, we would be like, wow, the model is basically linear. I think we're done. There's nothing that we need to do here. But notice what the residuals say. The residual is the difference between the observations and the prediction. And so what this says is that the difference between the observations and the prediction is essentially a quadratic. If it was exactly a quadratic, if we knew it was exactly that the linear model minus the linear model predictions minus the observations were quadratic, then what this would mean is that if the error equals if the errors are quadratic and the errors are equal to the linear model minus the observations, then what this means is if we add a quadratic term to the model, we should have it exactly. Now we can see here that this is not exactly quadratic. In fact, each measurement, there's a load measurement. There's two measurements for every load, so we don't have something that's exactly quadratic because we have, different loads giving different values, right? But the point is, it looks almost quadratic, okay? And so now what we're going to do is we're going to try a quad fit. So instead of doing a linear model or a constant model, we're going to do a quadratic model. So that's what I'm doing now. I'm going to do a quad is equal to NP dot polyfit and degree 2 here. Okay, so now I'm just going to let Gemini I'm going to let it do its thing. Y quad, okay, perfect. And then E quad is equal to Y, perfect. And then now I want another row, so I'm going to add a 3 here. Okay, and I just want to see what the plots are going to look like. Okay, so notice that I have this thing here where the labels are running in. The way to do that is before we show, we're going to do plt dot tight layout. Honestly, I've never looked in much to what exactly this is doing, but I know what it does is it gives me, it makes it so these labels don't run into each other. I'm going to just fix this before I even plot the other thing. And I want these graphs to maybe look a little bit more like that. So let's see if we go up to 18. Okay, so perfect. And now what we're going to do all of the, axes, the 2 index row, 0th column, dot scatter x, y, label equals observations. Whoops. Axes 2, 0. Okay, all of this, x, y quad, colors equal to green, labels a quadratic model, all of this stuff we got going on down here. We're going to set the title to be quadratic model, everything that we just did up there, but for the quadratic model. Okay, and all of this right here. Now I need to set the label for the residuals, which is exactly what we're going to do here. In the old days, before Gemini, and I was doing something like this, I would just copy and paste. But Gemini is even faster than copying and pasting. Okay, now this is great. Over here, we don't have like a discernible pattern. If we had a pattern that looked like it could be a cubic polynomial, then maybe you would go ahead and look at a cubic polynomial as well. Okay. So this is great. There are 2 important things to mention. The first important thing to mention is that the model looks great, but we really need a quantitative way to tell how good the model fits. This is for 2 reasons. 1, looks can be deceiving, but 2, we might be dealing with higher dimensional data, and plotting these residuals might not be so easy. Like x could be a 2-dimensional, as we'll see in week 2. X itself could be an R2. And so this is going to be, the residuals would be a 3-dimensional plot of a 2-dimensional variable. Okay, well, what happens if x has 5 components to it? Then plotting just doesn't make any sense at all. So we need some way to give a quantitative measure of how good this fit is. And that's exactly what we talk about down here. So we have the RSS, MSE, and RMSE. So the first thing that we want to talk about is the total sum of squares. So what is this? So we're going to look at YK minus the average of y and square it. This is almost a sample variance, and it is like the sample variance. It is a measure of the observations about their mean. And so it says, okay, there's some variability just in these observations, and this number, TSS, sort of tells us about the inherent variability in those. Now, what is RSS? So RSS is the residual sum of squares. So that is the kth residual right there. YK hat is the prediction, YK is the observation. So we're going to do YK minus YK hat squared. Now, this tells us, after we do the regression, how much variability is not explained by the model. Okay, because we're subtracting out the model here. So it's the variability that is not explained by the model. Okay, and we'll see more about this when we get down to R squared in just a minute. Now, why, the problem with RSS here is that if you have a huge data set, the residuals could all be very small, but there's just so many of them, RSS is large. So the mean squared error is just to do the residual sum of squares and divide by 40. Okay, whoops, what? I wish I hadn't done that. What did I do wrong? Because, okay, sorry. Now, the difficulty with MSE is that its units are not the same units as y. It's the square of the units as y. So to get it to the same units, we take the square root, and that is the root mean square error. The R stands for root, not residuals. Okay, and so what we're going to do is we're going to display these statistics below. I don't want to write everything because I'm running out of time here. So I'm just going to copy and paste and explain what's happening here. So, actually, you know what? I just don't need to do is, I will write everything. Okay, so I want a table, okay, of these datas. So RSS, a table of these datas. That's not what I wanted. Okay, RSS constant is going to be equal to np dot sum e constant squared. Okay, so what's going on here? Constant. So e constant are the residuals. For RSS, I need to add the square of the residuals. So since e constant is a numpy array, when you do this star 2, that is a numpy thing. Like star 2 means multiply every entry by 2. Star 2 means raise every entry to the second power. So that's what the RSS for constant is. And then we're going to do RSS linear is equal to np dot sum e linear, and then I'll let this take over. Okay, so what is MSE? MSE is just RSS divided by the length. So that's what we have here. And then what is RMSE? RMSE is just going to be equal to the square root of the MSE. So that's what we have here. Okay, now you could just like print each one of these out, but I've shown you how to arrange it into a table here. So rows is going to be a vector that contains our rows. We're going to start it off as an empty vector. And then now we're going to append rows. So rows dot append. Okay, so we're going to add a row, and here's the row that we're going to add to this. It's going to be constant. And why we're doing it in this order will make sense when we view it. RSS constant, MSE constant, RMSE constant. Okay. And then now we're going to do the same thing for linear and that. Okay, so this gives us some rows, and now we want to turn this into a data frame. And so now we're going to do errors is equal to PD dot data frame. So this is like if you know object-oriented programming, it's not necessary, but if you know object-oriented programming, this is like a constructor. And so errors is going to be a data frame that's returned by the data frame constructor. So we've got rows and then columns, rows. The columns are going to be equal to model RSS MSE, whoops, MSE, RMSE. And then we want to show the errors. So print. Okay. Okay, so this is good. If we see what happens as we move through the linear to quadratic, the RSS gets smaller, the MSE gets smaller, and the RMSE gets smaller. The RMSE is one of the most relevant measurements here. Notice that the linear fit looks pretty good, but if you look at the RMSE, there's about the RMSE for the linear is about 10 times as bad as the RMSE for the quadratic. So even though from the linear model it's a little bit difficult to show, and even this model doesn't look too much different than this model right here. This is the quadratic model. It doesn't look too much different than the quadratic model, the quadratic model here doesn't look too much different than the linear model. Quantitatively, the RMSE is about 10 times worse for the linear in the sense that it's 10 times the RMSE. Now we don't want to come over here and look at MSE and say there's a 2 magnitude difference, or over here and say there's about a 2 magnitude difference. And the reason is that these are not measured in the same units as y. So this is the sort of quantitative comparison that we want to make. Okay, R squared statistic. As I said above, TSS is the inherent variability. RSS is the variability not explained by the model. So TSS minus RSS is the variability that is explained by the model. And the proportion of total variability, if we divide by TSS is like the total variability or the total variance about the sort of, it's a measure of the total variation of the observations around the mean. So this is the observations around the mean that are explained by the data. And so if we divide by TSS, this number right here is the proportion of variation of the observations around the mean that is explained by the model. And as we can see, RSS is going to be less than TSS. I guess that's something that you would have to prove. RSS is less than TSS, okay? And so what this tells us then is this number right here is always going to be between 0 and 1. So the closer to 1 this is, it means the more of the variation that is explained by the model. Okay, so now what we're going to do is just look at the R squared statistic. So we're going to do R2. We're going to do some copying and pasting again. Okay, so this is what we have here. This does not, yes, okay, R2 quad. I forgot R2 constant, sorry. R2, there we go. Okay, so now what we're going to do is we're going to append I'm actually just going to I'm just going to do this again. Okay, so now we're going to do R2, and then down here we're going to do R2, and then down here we're going to do R2, and then we're going to add R squared. Okay, and so we can see, we have a very good R squared for the linear, but, for quadratic, to the precision that we have here, it's 1. So obviously, the quadratic is much better. So one of the things that data is showing is that actually, if we are going to use this in real life, we really need to use the quadratic model because the RMSE is so much bigger. The RMSE is about 10 times bigger for the linear than quadratic, and we have, a 1 correlation coefficient here. Okay, the second important, so I just said there are 2 important things to think about. That was one thing, the quantitative look at the errors. The second important thing is calibration versus validation. So what we've done now, we've taken our data and we have fitted a model to it. We fitted a quadratic model. But a question that we can always ask is the model actually telling us any information, or is it just producing what we put into it? So the common way to get the common way to fix that problem is to calibrate the model using one set of data and then validate it with another set of data. And it actually works out very good in this problem. Okay, why do things work out good for this problem? Things work out well for this problem because for each entry we have two measurements. So if we come down here, we have a measurement for 15,000 or 150,000 there and 150,000 there. So the table is already split into like a calibration and validation. So what we're going to do is we're going to use these data right here to calibrate our model, and then we're going to overlay it. We're going to test it against these data right here to see if the validation. Because again, what should happen is if we use this model to calibrate our data, it should be a good prediction for what happens here as well. So that's what we're going to do next. Okay. So I'm using slightly different variable names here than I have in the notes. So I'm going to do x x calibration is going to be equal to x20. So what this means is going to go, it's shorthand for this, and what this means is going to look at the entries of x for index 0 up to, but not including index 20. So I'll have index 0 through 19. And then if you don't have anything there, it's just automatically 0. Then I'm going to do x validation. Whoops. X validation is going to be equal to x. We're going to start at index 20 and go up to the last thing. If you don't put anything there, it says we're going to go up to the last one. Now y calibration is going to be y. Okay, exactly like this. Perfect. Okay, so now I need to make the models. So I'm going to say a constant. And now I need to make my model only using the calibration data. And that's exactly what this is doing right here. Okay, constant, linear, quadratic. I'm making my model only using the calibration data. So now I have my model. So now what I need to do is I need to start to validate my model. So now what I need to do is I need to apply the polynomial to the validation load data. Now in this case, xcal and xval just happen to be the same numbers, but it could be the case that maybe here we have calibration for 15 up to 3 million or whatever that is, and then maybe the next set of data, maybe instead of 15,000, it's like 16,000 or something like that. So for validation, I'm going to say y, constant is equal to np dot polyval. And see here, Gemini's giving me the wrong thing. Oh, no, it's not. It's giving me validation. Never mind. Okay. Gemini did not give me the wrong thing, though sometimes it does. Okay, so now what I want to do now is we can look at the residuals as well, just to see what the errors are. So I don't, yeah, okay. Yep, okay, this is what I want here. Y, the validation y's minus the constant y's. Okay, and now, well, I'm just going to fig axes is equal to PLT. Okay, perfect. This is giving me everything that I want. Okay, and so now what I want to do is I want to plot the validation y's and I want to do a scatter plot with the x validations and the y validation. The x val and the y val. That's the validation data, and I want to plot the model on top of that. But remember, importantly here, the model was not created by the validation data. It was created by the first 20 rows for the calibration data. Okay, so we are not. It is not the. We are not plotting the model was fitted on the calibration data, and we're going to plot it over the validation data. And so, if our model is a good one, if we're calibrating it on one set of data, then when we look at it and validate it on another set of data, it should be a good prediction for that data as well. Okay, so think about what I'm saying here. If we just have a model and we fit a model to our data, there's always a question of, does this model does the calibration of this model, is it just calibrating to the data that we're giving it, and it's just reproducing stuff in the data, right? What we want to do really is saying, is there something underlying going on here? And if there is something underlying going on here, we're going to be able to get the coefficients from one set of data, and it's going to fit to the validation data, another set of data. Okay, so now we're just going to do some plotting here. Okay, so we're going to do axes. Okay, so this gives us everything that we want here. Perfect. X validation, Y validation, scatter, X val, Y val. Yeah, okay. And then we're going to do, whoops. I don't know why it stopped and didn't give me the Y label. Okay, there we go. Okay, so axis 0, 1, we're going to plot the residual. Okay, so here we go. All right. Okay, so let's just look at this to make sure it's going to give me what I want it to. Yep, okay, that's what we wanted. Okay, perfect. Then we're going to do axes 1, 0. Okay, dot scatter. Okay, perfect. This is just sort of repetitive, a lot of the stuff that we've already done. Okay, perfect. I didn't do the label here, did I? Okay, whoops. Okay, so now okay, so perfect. Okay, we'll plot this and then we'll talk about it, and then finally axes 1, 0 dot scatter X val. Okay, axes 1, 0. I think Gemini's getting tired now. Okay. And then we've got, okay, but notice this is not what we want here, so I made a mistake. It's okay. And it's not, because I'm doing 1 and I should be doing 2. It didn't make a mistake. I made a mistake. Okay. Well, I'm sorry, Gemini. Don't get me. Okay, so there we go. And then we're going to do... Okay, so again, what we've done here, this is the linear. Okay, this is the yeah. So there's something strange about the scrolling. So this is the linear model. This is the quadratic model. Let's just look at both of these. So notice what we've done here. We have calibrated the data on the rows 0 through 20, and now we're validating it, or sorry, 0 through 19, and now these data right here, these come from rows 20 through 39. That is the second set of 20 rows. And so what it's saying is that the model that is calibrated, that is, we're using these data right here to come up with the coefficients on the polynomial, it still fits these data right here, which tells us that our model isn't just reproducing some feature, maybe some noise within the data, but what it is doing, it is actually picking up, is actually a good model for what's happening here. We could just say, let's get higher and higher degree polynomials. What happens though is if we get higher and higher degree polynomials, that is going to start not really capturing a property of the model, but more the properties of the noise in our system. But what this is saying is that for the, that should say quadratic. No, okay, never mind. We got linear and quadratic. So what this is saying is for the quadratic model, for what we have here, since we fit the model using calibration data and we test it using the validation data, and it still is a good model. The model that was fit using calibration data fits well the model, the validation model. It fits the validation model well, and so this gives us confidence that we have a good and robust model. And you'll be doing this in your homework.